So far, whatever we've seen was in context of a single database node, how to achieve ACID compliance for that single database node and various indexing techniques for that single database node. Let's expand this in a distributed setup by having more nodes into the picture. So in comes a replication. A replication is basically you have your primary database where your reads and writes go, and you have replicas of all the data stored in your primary DB. So the picture shows 3 replicas, R1, R2, R3, which is essentially data backup of whatever is stored in the primary DB. So this has many use cases. Number one is obviously fault tolerance. In case the primary DB goes down, you always have a fallback in either R1 or R2 or R3. Another one is increased throughput. So throughput is the amount of operations computed per second. So rather than having your primary DB as the sole bottleneck over here, you can distribute your requests to your primary DB and the replicas as well. The third point is low latency in terms of the requests processed. So assuming you have your users located all across the globe and your replicas also are in different regions across the globe. So your Asian user can direct their request to the node situated in the Asian continent. And all this obviously leads to higher scalability. Now let's assume for a second that our primary DB hosts some data and that same data is located in R1, R2, and R3. Now read requests are very trivial to serve over here. All the data is the same everywhere, and that read requests for different users across different geographies should be the same. What if you get a new write request? So let's say that write request gets directed to the primary DB. Now suddenly your overall state is inconsistent. So your primary DB's responsibility is to forward that write to the other replicas. So there are broadly two ways in which you ensure consistency when you serve write requests. The first way is through synchronous replication. So synchronous replication, assume that this is your application server. You get an incoming request to update the value of X to 5. And let's say the current state of the system is X is 3. So this is your primary node with X is 3 and your replicas also has X is 3. So in synchronous replication, its main objective is to ensure strong consistency. That means at any point in time, no database node should hold stale or incorrect data. So let's say your application server gets X is 5. So before submitting a commit successful message to the application server, your primary DB will send X is 5 to all the replicas. And only when it gets a success response from all the replicas, it will send a success to the application server. So stale reads over here are not possible. So after your X is 5 write, any two users, when they read the value of X, let's say their read request goes to any replica node, those users should get the same value of X, which is 5. You should not have a user getting X is 3. The state of the system for any user reading from any node should be the same. Now the obvious drawback for this is any new write that comes in, before confirming that write to the user, we have to touch all our replicas. And if our replicas are pretty large in number and they're pretty distributed geographically speaking, this is a pretty high latency operation. So another mode of replicating is through the asynchronous means, where we don't care about strong consistency from the get-go, but we are fine with eventual consistency, where stale reads are possible, but they don't impact our application in a very critical way. So in this case, our initial state is X is 3. Our application server sends X is 5 to the primary node, and the primary node will obviously update itself and immediately send a commit success message. And in the background, eventually it will update the replicas with the latest value. So what is the drawback over here? The drawback over here is you will get inconsistent reads. So let's say user 1 then reads from this primary DB. User 1 will get X is 5. And then user 2 will read from one of the replicas. They will get X is 3. So the overall state is inconsistent. So it all ultimately boils down to CAP, as we saw in the first video. So if your system favors consistency, we'll push towards the strong consistency model. And if it is necessary that we need high availability at all times, we move towards the asynchronous model. We'll see more details towards the end of this video. So how do we actually replicate the latest state? The first means is to push the SQL statement to the replica. So if you're getting a write, update x equals 5, where ID is this, then just forward that SQL statement to all the replicas. Pretty straightforward. But there is one problem, and that SQL queries can be non-deterministic in nature. Let's say you have to insert the username and the current time as a login time. So current time you're using some time library, time function, time.now. This is non-deterministic in nature. You will be inserting 100 milliseconds, but when you forward the SQL statement, the replicas will insert whatever the current time is. It could be 200 milliseconds. So it's non-deterministic in nature, and we generally don't do this. The second means is to push the write ahead log. So if you recall, the write ahead log is maintained for fault tolerance. What I did not mention in the previous videos is that the write ahead log is very fine grained, and it contains very low level, byte level operations which are very specific to the disk. So rather than thinking that the write ahead log contains entries like x equals 5, what it actually contains is byte level, disk level operations. For example, at this particular address, the value is going to be 13, or delete this specific byte. So what is the problem with this? The problem with this is it requires all the replicas to have the exact same database, the exact same disk, the exact same storage, the version, all of them should be the same. Only then do these addressable entries make sense. So this is obviously not a favorable approach when you talk about large scale systems. So we'll go towards the third approach, which is to maintain another log, which is again on the disk, just like the write-ahead log, but this one is not going to be as fine-grained. This is going to be in a much higher abstraction level, and it's going to contain operations as we know it to be. For example, update this specific ID to 5. So rather than containing addressable entries, it will contain entries corresponding to a particular ID. So update ID is 5, delete record with this particular ID. So the drawback for this is obviously, in addition to the write ahead log, you're maintaining another log, and this is on the disk, and you'll have to deal with that disk read write operations. But on the whole, this should not be a deal breaker. Replication logs are actually used in practice, so let's go along with this for now. Now we saw that one drawback of the eventual consistency model through asynchronous replication is that we have stale reads. Now stale reads by themselves is just a phenomena that different users read different data. But stale reads can also lead to some consequences or some anomalies. And let's take a look at 3 anomalies. One is read your own writes. The second is monotonic reads. And the third one is consistent prefix reads. So let's talk about read your own writes. So in read your own writes, let's say you're writing a comment on an online blog. So you just submitted your comment, and now you refresh your page, and the expectation is that you should be seeing your comment that you just wrote. That means read your own writes. Now, why is this a problem in asynchronous modes of replication? So let's say you wrote your comment and it's plugged into the leader node, and let's say it's also replicated in this replica 1, but it's yet to be replicated into replica 2. Now, when you do an immediate refresh and then you do a read again, let's say the load balancer will route your request to replica 2, but replica 2 is not yet replicated with the latest data. Let's say it gets refreshed after 10 minutes, but now you've lost your latest write that you just did. So this is obviously not a good user experience. So what are ways that we can achieve to help mitigate this? So the first solution is the client gets routed to the node that it just wrote into, the leader node, for the first X duration until all the nodes are replicated. Now over here, you can have multiple application servers, server 1 and server 2. And let's say initially your request goes to server 1, your write request, and server 1 will forward it to the leader node, which is DB1. When you refresh your, let's say your read request will go to server 2. And how will server 2 now know that it has to forward your request to DB1? So we need to store this information somewhere. And what is often used in practice is we make use of a distributed cache like Redis. So when your write first goes to server 1 will make a note in Redis that for this particular user, route it to this DB1 up until time 10 p.m. Then when your read request goes to server 2 will first check with Redis if you are in the entry, and if you are, it'll route you to the respective DB. So obviously one downside is the introduction of Redis over here. You have to read from Redis for every single read request. That aside, another downside is the X time window. I will be making multiple references throughout the video, but when you deal with time, as in epoch time, they are very inconsistent in a distributed setup. And it's because times are unreliable when you talk about extreme preciseness. Different nodes can have differing times. And when I say differing times, I don't necessarily mean they differ in hours or minutes or seconds. They could differ in terms of microseconds or nanoseconds. And why is that? The time is determined by a quartz crystal oscillator in a computer. And this is a mechanical device, and over time, the frequency can change. So the time that you're getting can distort when you compare it with some other node. So while they won't differ in terms of hours or minutes, but if you run a very time critical mission intensive application, for example, financial applications where even nanoseconds matter a lot, this could be a problem. So we generally don't go with physical time for critical applications, but for most applications, this should be fine. The second solution to ensure that you will always read your own writes is to pass your last write time for that ID along with your subsequent reads. So let's say for the subsequent read, you say that your last write for this ID was 10:01. You'll pass it to your server. Now your server will query with each replica, when was the last time you were refreshed? When was the last time you were replicated? So this one over here says that it last replicated at 10:05, but your last write was at 10:01. So it's bound to contain your latest write. So your server will direct your read request to it. Again, just like anything, while this is a good approach, this also has limitations because we have to query each replica to ensure its last sync time corresponds to your last write time. The second anomaly deals with monotonic reads. So if you're familiar with monotonic, it means basically increasing over time. So your reads should always go forward with time. You should not read back in time. They should be monotonically increasing. So when can this happen? This can happen if a user makes several reads in a short time, and these reads get routed to different replicas. So let's say you've written 3 times, write 1 and then write 2 over time and then write 3. So initially when you're trying to read, you read write 1, that's fine, that's the latest write. And then you hit read again, you read write 2, which is the latest write over here. But then the next time you hit read, you're not reading write 2 or you're not reading write 3. You're going back in time to what you've already read. This could be because you're reading from a replica which is not yet updated with write 2 or write 3. This replica still has write 1. So your third read is going here. So one very trivial example could be you're reading person A's comment on a blog, and then you hit refresh, and now you're reading person B's comment to person A's comment. And when you hit refresh again, now person B's comment is gone. You just have person A's comment. So you're back to square one. You're reading back in time. This could be because your third request was routed to a shard, was routed to a replica which did not have person B's comment. So how do we prevent this? So solution one is to try and route the client to a single node always. You can have hashing over here. So based on the hash of the client ID, route it to a specific node. The drawback to this is what if the hashed value, the replica that you're always routing it to, it dies. So now you have to reroute it. So after rerouting, this can go to a node, which is again having a stale entry. The second solution, assume that this was your original entry over here, x is 5. This was version 1, and then it got updated to version 2, which is x is 6. Now for subsequent reads, let your client send the data that they're reading, the ID that they're reading, along with the last version that they saw, which is version 2, to the application server. Then it's the application server's duty to ensure that whatever replica it routes your request to contains at least version 2 for that ID X. So just a side note, you can pass the physical timestamp with the last read that you did. So you can pass the last read was done at 10 p.m. That is fine. But as stated earlier, clocks are not reliable in a distributed setup. So what we actually use in practice most commonly is these versions like v1, v2. We call them logical timestamps. So these versions are monotonically increasing with time, just like physical time that increases as time progresses. These logical timestamps also increase with time, v1, v2, v3. We'll talk about logical timestamps in the next video in great detail, but for this video, let's assume that these versions that we're tracking v1, v2 is very equivalent to the physical times 10 a.m., 11 a.m., so on and so forth. Let's talk about the last anomaly, which is consistent prefix reads. So these come into picture when we talk about replicating two partitions. So what is a partition? So assume you have one database which stores the names from A to Z, but the values get too large to be contained in one node. So what you do is break the data into multiple nodes. You partition the data into multiple partitions. So one partition can hold A to H and the other partition can hold names from I to Z. So the basic premise of consistent prefix reads is that you want to avoid out of order reads when you're reading from these partitions. Let's take a look at it with the help of an example. So let's say A first sends this message to B, hello B, how are you? And B in response to A's message will say, hi A, I'm fine. So objectively speaking, we know that the order in which these messages, these events came was A first, and then B's message was a consequence of A's message. So B is dependent on A, or in terms of distributed systems, we say that B is causally dependent on A. The event was causally dependent on a prior event. Now, let's say these events, these messages are stored in different partitions. What we need to do to ensure that we have consistent prefix reads is when we read from the partitions, we read A first and then B. We don't read B first and then A. The prefix, the order in which the events happened, the prefix should be consistent for all the users when they read from the different partitions. Let's take a look at another concrete example that will drive home the picture even clearer. So Mr. Poons over here initiates the conversation to Mrs. Cake by saying, how far into the future can you see, Mrs. Cake? And Mr. Poons pushes this message onto partition 1, which is the leader. Now Mrs. Cake is subscribed directly to the leader partition 1. So Mrs. Cake will immediately receive the message, how far into the future can you see, Mrs. Cake? And she responds about 10 seconds, usually, Mr. Poons. And when she responds, she will push that message to partition 2 leader. And now Mr. Poons is also subscribed directly to partition 2 leader, and Mr. Poons will then immediately get the response. So far, so good. But now let's say you have a third party over here, the observer. Now when Mr. Poons pushes, how far into the future can you see, Mrs. Cake, to partition 1? Partition 1 leader asynchronously in the background will obviously try to replicate it to its follower, which is over here. But let's say this follower is in some other continent and it takes time to reach partition 1 follower. But in that time, Mrs. Cake has already received the initial message, crafted a response, pushed it to Mr. Poons through partition 2. And now partition 2 leader has also replicated it to partition 2 follower, which is, let's say, pretty close by to partition 2 leader. Now the observer is subscribed to both partition 2 follower and partition 1 follower. But when the observer receives the message, observer will get B first instead of A, will get Mrs. Cake's response first instead of Mrs. A. So if some partitions are replicated slower than others, an observer may see the answer before they see the question. So the order in which you see the messages should be in a consistent order. It should be causally dependent, causally consistent. You should see A first and B, which was causally dependent on A. So how do you ensure this? So one solution is push causally related writes to the same partition. So let's assume that you make a comment on a Reddit post, and then let's say this is comment A, and then comment B, comment C, comment D are all responses to your initial comment A. So B, C, D respond to your original comment. Now, obviously, we can infer that B is causally dependent on A, C is causally dependent on A, so on and so forth. So for this use case, what I can do is in the same partition, I'll push message A, I'll push message B, I'll push message C, D, so on and so forth. So push causally related writes to the same partition. But this is easier said than done because it's not very easy to identify uh, events which are causally dependent. This is very trivial over here in this case. Secondly, what if the thread becomes pretty long? Like let's say you'll have 1 million entries over here. So it'll be a bottleneck to store all those 1 million causally dependent entries on the same shard. So this is not a good approach and we don't do this in practice. The second approach is to use version vectors. Now, version vectors are a data structure, which is basically a vector that helps us detect causal dependencies. So what does this mean? Let's go with the same example. We have partition 2 follower over here, and we're trying to write Mrs. Cake's response here. So this is message B. Now, with the help of version vectors, while writing B, we can tell P2 that, hey, P2, you're missing A's initial message. So store A's initial message and then store B's initial message. You can do this with the help of version vectors. I'll go into version vectors at a very high detail in this section. We'll revisit this when we talk about multi-leader setups later in this video. Feel free to revisit this section once you get a better understanding of version vectors when you discuss it later. So let's see how version vectors help us detect causal dependencies and help maintain causal dependencies in a particular node. So in this case, when you're writing B, you're storing A first and then B. So you want to maintain the causal dependency in the particular node. Let's see how it's being done. So the way version vectors are maintained is it's a normal vector. And let's say you have 2 nodes. Then the vector will have 2 entries. The index size will be 2. And all the nodes in your system will have the same version vector size. They'll all have a version vector of size 2. Each index over here corresponds to some node. So let's say this is node 1 and this is node 2. Let's say I am node A over here and I perform a write operation. In that case, I will increase my particular index. Let's say I do another operation, then I will increase my particular index. Let's say the second entry was for B. B means 0 over here. So what does this mean? 2 0. So 2 0 means I am A and I have done 2 operations. And I know that B exists in the system, but I've seen 0 operations from B's side. So I don't know whatever B has done. I've not tracked anything that they've done. Now let's say this was for A. Now B will also have a similar setup where this corresponds to A and this corresponds to B. So this is B's version vector over here. Now let's say B does some operation on that particular item. So it'll increment 1. Now A will be 0. So what this means, 0, 1. So B says, I know I've done 1 operation. So I marked 1 here, but I don't know anything that A has done. So A will be 0. Now, when you talk of asynchronous replication, these nodes will periodically exchange their version vectors to be in sync with each other. So when A sends its version vector to B, A sends 2 0. So what does B see? B sees that A has done 2 operations which it does not know of. So B will then finally update its version vector, and for node A sees that B has done 1 particular operation over here. So node A will also update its version vector. So the final version vector of both these states will be 2, 1. Now, obviously, alongside with updating the version vector, they'll also update the actual data. So they'll update x is 5 or x is 3, whatever value it is. So going with this level of understanding for now, let's say Mrs. Cake initially sends the message, hi, Mr. Poons, how are you? To partition A. So partition A will increment its index over here, and it has received no such event. It knows no such write that happened on partition B. So it will be 0 over here. And partition A's version vector will be like this. Now, Mr. Poons is subscribed to partition A. Mr. Poons gets that message, and it will also get the version vector, which is over here, A1, B0. Mr. Poons will then craft a response, hi, Mrs. Cake, I'm fine, and send it to another partition B over here. And when you're sending the message, you'll also plug in the version vector of the previous node. This is to maintain causal dependency. So when partition B gets the version vector along with the message, partition B sees that, oh, my initial state is A0, B0, and now you are sending me a message where A is 1. I don't know of any such write that happened from A. So what partition B will do is it'll query with partition A that, hey, give me whatever operations I'm missing. Partition A will then send this message, hi Mr. Poons, how are you? Partition B will store that. Partition B will update A is 1 and obviously increment its own index because it has to write this, hi Mrs. Cake, I'm fine over here. So when you have a third party that is reading from partition B already contains the message from A and B, and they can read both of them. By the way, quick side note, why is it called causal dependency? So A is the cause and the consequence of it, the effect of it is B. So because A is the cause of B, which was the effect, so we call it causal dependency, a dependency because of this particular cause. So to conclude with consistent prefix reads, it's not very trivial to implement. There's a lot of complexity involved in terms of storing the version vectors, transporting the version vectors along with the messages. And if you have a million nodes, your version vector's length will also be a million, and scale that to a million nodes. You have a million times a million. It is obviously bandwidth intensive when you package your messages along with these version vectors and transmit it across the network. So these are three replication anomalies when it comes to asynchronous replication. And we saw a couple of solutions for each one of them. And obviously the solutions will have their own trade-offs, but this should be good enough for now. Let's take a look at three architectures to implement replication. The first is single leader, the second is multi-leader, and third is leaderless. Whatever examples we've seen so far were along the lines of single leader replication. So let's go along with it for now. So in single leader replication, you have one leader node where all the writes go to, and the reads can be done from any node. So you have one leader over here, you have a bunch of followers, writes go to the leader will replicate the writes to the followers, but reads can be done from any node. So what are the benefits for this? Number one is increased read throughput. Reads can be done from any of these nodes. These nodes can span geographies. But a drawback is obviously there's a bottleneck on writes. All the writes have to go to one leader. There is a benefit for this. So assume we had two leader nodes that accept writes, and we have x is 5 over here, and then another user writes x is 3 over here. Now, how do you reconcile with the value of x? You have this merge conflict when you have multiple leader nodes. So that is avoided because you have a single leader set up over here. And the third benefit is it's very easy to implement. All you have to do is just modify your existing single database node to add in more follower nodes to it. So let's take a look at two failure scenarios. Number one is the follower goes down. So let's say the leader has till operations 80 in the replication log, and the follower has till operation 70 in the replication log. But before it gets a chance to update itself with the latest entries from 71 to 80, let's say the follower node shuts down. Number one is this shouldn't be a problem because you still have the leader node that accepts writes, and you have the other follower nodes that can serve your read requests. But let's say your follower node comes back up. It'll first try to sync with the leader, and with the help of the replication log, it knows that the last entry it was at is 70th operation. So the leader will then update it with the 71st to 80th operation. So recovery over here is very easy because of the replication log. What if the leader goes down? If the leader goes down, it can lead to two issues. One is lost writes and the other is split brain. Lost writes, your writes are literally lost in thin air. So let's say you have your user performs some transaction which deals with writing operations 71 to 80, and your leader node will obviously update itself and send an immediate commit success message. Now, before the leader tries to asynchronously send 71 to 80 to its followers, let's say the leader shuts down. it goes off. Now, the other followers don't know that 71 to 80th write happened, but these writes were technically committed and you sent a success message to the user, but they are lost now. So you have lost writes. So one solution is obviously to use a synchronous replication rather than asynchronous. You will only send a commit success message after you've replicated it to all the followers, ensuring that the write is persisted into your system. The second solution is to use quorums in tandem with a distributed consensus algorithm like Raft. We'll talk more about quorums in the later section of this video, and we'll talk about Raft in detail in the next video. So quickly, what is quorum? Quorum is basically a way to ensure strong consistency. Strong consistency is basically different users read the same data at all times. So let's assume you have 5 nodes over here. So n is 5. So quorum consistency basically demands that the reads plus the writes should be greater than n. So let's say R is 3, W is also 3, and 6 is obviously greater than 5. So what does this mean, R plus W greater than n? So when you want to write something, let's say you want to write x is 5, you will write it to 3 nodes, x is 5, x is 5, x is 5. And let's say the older version of x was 3. So x is 3 here, x is 3 here. So you wrote it over here. And when you're reading from 3 nodes. So let's say you're reading from this node, you're reading from this node, and you're reading from this node as well. So your number of read nodes plus the number of write nodes overlap. And let's say they overlap over here. Now, you know, when you read, you've read x is 3. Let's say it's also associated with a logical timestamp. Let's say this is version 1, and this is also associated with version 2. Now, when you're reading, you know that x is 3 comes from version 1, and I've also read x is 5. That's coming from version 2. So you'll obviously pick x is 5. So any read that you do, you won't just read one node and call it a day. You will be reading from a quorum of read nodes, which in this case is 3. And because of the way that you've picked R and W ensures that there is an overlap, and that guarantees that you will always be reading the latest version. Now, how can quorums help with lost writes? So let's say this is a leader node over here, x is 5, and the leader node will also propagate it to this node over here and this node over here. And let the other 2 nodes stay blank. Now the leader node goes down. By the way, the leader node will first propagate it over here, ensuring that the write node is 3, and only then send a commit success message to the user. So now the leader is down. In comes the Raft algorithm. So Raft is an algorithm to implement consensus among these distributed nodes. What does this mean? So when I talk about consensus in a distributed setup, the nodes are in sync, in consensus with who the current leader is. The nodes are in sync with which nodes are alive, which nodes are dead. The nodes are in consensus with what the latest version is. So all of this can be implemented with various algorithms. One of them is Raft and the other one is Paxos. So let's say you have your 5 nodes over here, and this is x is 5, this is x is 5, this is x is 5. We establish this through the write quorum. Let's say this is stuck at an older version, x is 3, and the leader node dies. Now all the other nodes will eventually come to know that the leader node died. How? Because they keep talking to each other. They establish consensus and they track their heartbeats. So they will know that, okay, the leader node is dead, and now we need to elect a new leader. So in the leader election process in a Raft, the other nodes will basically share what data they have. So this node will say, hey, the latest version I have is x is 5. This is v2. This node will say the latest version I have is v1. So all the nodes will basically understand what versions the other nodes have and pick a suitable candidate. So let's say this one gets picked to be the new leader. So once this is picked as a new leader, all the other nodes will be in consensus that the new leader for this session is going to be this particular node, and they will start receiving the replication log from this particular leader. We'll go into more detail about raft consensus in the next video, but this should be good enough for now. So we saw that even though the leader node goes down because you maintained a right quorum, the right is still there, and you still have a leader with the help of a raft consensus. Let's take a look at the second issue, which is split brain. So in this scenario, two or more nodes believe that they are the leader and both start accepting rights. So in split brain, basically, your single leader setup acts like a multi-leader setup. So let's say you have your initial database node over here with some other nodes over here, replicas, and this is the router over here, router or a switch, and this is the leader initially. This is another follower, let's say in some other geography, and it has other followers as well over here. Now, so far you still have just one leader, rights only go over here. But let's say you get a network partition, maybe this router breaks. So a network partition over here, and these nodes are isolated from these bunch of nodes. So what in effect happens over here is if you employ a raft consensus, these nodes will start gossiping with each other, try to gauge if the leader is alive or not, and they'll quickly determine that the leader is dead. And they will trigger the leader election within themselves, and they'll elect, let's say, this guy as the leader. Similarly, in this particular section, this guy continues to be the leader, and they both will independently start accepting write requests. So let's say the application server in this particular continent will direct the writes to this leader, and the application server in this one will start directing writes to this leader. So you'll have XS5 over here and XS3 over here. Now, if the router is restored back and the partition heals, then suddenly you'll realize that you have merge conflicts over here because of these split brains, these independent leaders taking separate decisions, and resolving these merge conflicts are not trivial. So the solution for that is again quorums with raft consensus. So let's say you have 7 nodes over here and 3 nodes over here, and the quorum, the majority nodes, are selected to be from this first group. In that case, the leader will be elected here. Group 2 is unable to form a quorum. Majority nodes are not available here. So group 2 will start rejecting writes. So using this, because you're discarding writes, there's no leader over here. You just serve stale reads. This gets no new write requests. The only leader will be over here in that section where you're able to form a quorum of nodes. Another solution is to make use of a central coordinator. So this one over here is distributed in nature. All the nodes will talk to each other and find out if the leader is alive or not. And if it's not alive, the nodes will decide among themselves only who the new leader should be. That is distributed consensus. Another approach is to use central coordination rather than distributed consensus. So over here you have a central coordinator like a class monitor, and Zookeeper is a pretty popular central coordination service. We'll talk more in detail in the next video about Zookeeper and the differences between distributed consensus and central coordination. So here Zookeeper basically will keep track of the status of the different nodes and also help in the leader election process. So step 1, your leader dies. Zookeeper will obviously notify the others, and the others will then send in what their latest version is, their latest state is. And all of this is facilitated through Zookeeper as a middleman. Eventually, one node wins and will check with the others, and upon receiving approvals from all the others, it will be the new leader. So the basic difference is raft, self-detecting consensus. The nodes themselves will detect the failure of the leader via timeouts, via heartbeats, and they will elect the new leader among themselves based on the latest state. Zookeeper, you rely on this central coordinator, this monitor, and Zookeeper will help detect leadership loss and will help trigger the leader election process. So the conclusion is, in single leader replication, if the leader goes down, you're susceptible to lost rights or split brains. And the solution for that is to use quorum-based consistency in tandem with distributed consensus like Raft, or you can rely on a central coordination service like Zookeeper. Let's talk about the second architectural setup for replication, which is having multiple leaders. So in a multi-leader setup, you'll have leader nodes where each leader node can take in both reads and writes, and each leader node will have an array of followers. So let's say A over here is a leader node. If it gets a write, its job is to obviously propagate it to its followers over here. And in addition to that, also send that particular write to the fellow leader nodes. Now, one major upside to using such a setup as compared to a single leader application is if your overall workload has a lot of reads as well as writes. So you can distribute that evenly across the nodes over here because you have multiple leader nodes, and you'll have more read and write throughput. Your writes are not bottlenecked by a single node. A drawback to this is because you have multiple nodes that can take in writes over here, you're prone to merge conflicts. So if A takes in a write to this particular key X and you have a simultaneous write to B, then resolving this during the syncing time needs some merge conflict resolution. It's not very easy to implement. Before we dive deeper into multi-leader setups and the anomalies, let's first understand what we mean by concurrent writes. So concurrent writes happen on two or more database nodes. So concurrent writes does not mean that the writes happen at the same time. This is different from concurrency and multi-threading. Concurrent writes basically mean writes that happen across two nodes, and these writes don't know about the other write that's happening. So for instance, let's say DB1, you're writing X is 5, and after 10 minutes, let's say you're writing DB2, X is 3, but DB2 does not know that you wrote X is 5 on DB1. So these writes are called concurrent writes. So concurrent writes are conflicting writes and they're unaware of each other at the time of writing. So you initially wrote X is 5 and after some time you write X is 3. Now this X is 3 is unaware of the X is 5 write that you wrote on some other node. So the X is 3 write is a concurrent write or a conflicting write. Concurrent does not mean simultaneous at the same time. It just means conflicting in a replication context. So why is it conflicting? Now, when you wrote X is 5 and then you wrote X is 3, which was a concurrent write at the time of replication, you have merge conflicts. So this is a conflicting write because DB2 did not know of the previous write, which was X is 5. So X is 5 came first if you look at it objectively, and then X is 3, that new write that came in after 10 minutes. So you can say that X is 3 was causally dependent on X is 5. X is 5 was the cause and the effect afterwards was X is 3. So dealing with concurrent writes becomes very tricky when you have these multiple nodes contain writes. So let's look at 2 or 3 solutions to deal with merge conflicts, concurrent writes. Solution 1 is to use last write wins. So over here we saw that objectively DB1's X is 5 write came first. So let's say it came at 10 a.m. and this came in at 10 a.m. X is 3. And when you plug in the value X is 5, you'll also associate it with the timestamp. Now, when it comes time for replication, DB1 will send its data to DB2, DB2 will send its data to DB1. And then they'll see that, okay, there are conflicting writes for the key, which is X. And then in order to resolve it, they'll use last write wins. So the last write was done on DB2 for X is 3 at 10 a.m. So that wins. So both the nodes will agree that X's value should be 3. The problem with using last write wins is you're relying a lot on timestamps over here. And over here, with the example I gave, 10 a.m. versus 10 a.m. Over here, clock skews won't be that pronounced. But as I mentioned earlier, clock skews won't be in terms of hours or minutes. It could be in terms of microseconds or nanoseconds. So in that case, it's not a very good idea to rely completely on physical timestamps. So a concrete example for this is, let's say you log into Amazon on your laptop and you request a quantity of 10 for some product. And then let's say a second later, you think that 10 is too much. So you go onto your mobile phone application and let's say replication is not yet done. And your mobile phone application's shopping cart shows that there are no products added. So you add that same product with 5 quantity. Now at the time of replication, when replication is done, you end up seeing the end product being that same product is 10 quantity instead of 5. Maybe because your mobile phone's clock drifted too far. So this is obviously not an ideal setup and it hampers user experience. So relying on physical timestamps is not suited when it comes to last write wins. Another approach is to use version vectors. As we saw earlier, version vectors help detect causal dependencies, and as a consequence, they also help detect concurrent writes. So let's understand this with the help of a distributed counter example. So let's say you have multiple nodes, and these nodes are basically a counter. So let's say I go to a website and there's a big button saying increment, and I click that button increment, and that the end output should be I should see my number increasing as I keep clicking on this increment button. And each time I click on this increment button, my request can go to different nodes. So it's a distributed setup for a counter. So let's say you have node 1 and node 2. I click on increment 3 times, and those first 3 requests go to node 1, and then after some time I click on increment 5 times and goes to node 2. So node 1 will have count as 3, node 2 will have count as 5. After some time, they'll replicate. Now, what should the end outcome be? What should the final value of count be across both these nodes? It should obviously be 8. So the new value should be node 1's value plus node 2's value. So now it's 8 and 8. Let's say after some time, I click on increment 5 times and goes to node 1, and I click on increment again one more time and goes to node 2. Now over here, it's 13 and 9. Now when they replicate, what should the new value be? Should it be 13 plus 9? No, that should not be the case. You should also have knowledge of what your previous state was. So when they sync, you need to have more information. So we need some more tracking data along with just the counter value, along with just the state. So we use version vectors for that. So node A will have in its version vector 2 indices. Same with node B. The first index corresponds to A, the second corresponds to B. So when you see 3, 0, it means node A has done 3 operations, but it knows of 0 operations done by node B. Similarly, node B knows of 0 operations done by node A, but it has done 5 operations. When you look at version vectors over here, 3005, you can instantly tell whether you have a conflicting write, a concurrent write or not. Let's see how. This one over here, let's say is 5, 7. And this one over here, let's say is 5, 2. These are not concurrent writes because the first vector overpowers the second vector in every metric. Let's take a look at another example, 0, 1, and let's say 2, 3. These again are not concurrent writes because the second vector overpowers the first vector in every way. I'll come into what the actual meaning of this means. Let's first understand how to detect if something is concurrent or not using version vectors. Let's take a look at a third example, 3, 4, and let's say 5 and 1. This one over here is a concurrent write. It's a conflicting write because no particular version vector completely overpowers the second. When I say overpower, I mean all the values over here should be greater than or equal to the other vector. Let's take a look at this particular example. Let's say node A has done 7 writes and it saw only 2 writes from B, and B has only done 2 writes, but B's node has only seen 3 writes from A. Now at the time of replication, node B will send its version vector to node A, and node A sees that, okay, it is clearly better than node B. It has seen more writes in node A, obviously, as well as the number of writes in B is matching. B has not done any new write. So node A does not need to update its value or grab any more information from B. Node A is clearly superior. Simultaneously, node A will also send its version vector to node B for replication, and node B sees that, okay, the version vector sent by node A is clearly superior to me. It dominates me on every aspect. That means whatever value node A is storing for X is the latest and greatest value, and B will simply grab that value of X and patch it to itself. So in this case, this completely overpowered this. This was not a concurrent write. A objectively had the better latest state. Let's tweak the example a slight bit. Now let's have 5 over here instead of 2. Now clearly this is a concurrent write, a conflicting write, because no one vector completely overpowers the other vector. A has seen 7 writes. It has seen the latest and greatest state compared to for A, but it has only seen 2 writes from node B, but node B has clearly done more writes. Node B is also lacking. It has not seen whatever subsequent writes were done to A. There were 4 more writes done to A. Before we go to how these version vectors will reconcile differences between them, let's understand what this actually means. What is the physical meaning of 3572? So let me reduce the numbers a bit. Let me make this 3, 1, and let me make this 2 and 2. So again, these are conflicting over here. No one version vector completely overpowers the other. So this is node A and this is node B. What does this mean? The physical meaning. Let's start with this state. This is A, this is B, and initially A does one write, so the X value is 1, and then A will do another write and the X value is 2. Simultaneously, on the other hand, parallelly, let's say B will also do one write, so the X value here is 1. So the equivalent version vectors will be 2, 0 over here, and it'll be 0, 1 over here. Now, when they try to sync, they'll come to know that, okay, the version vectors over here are conflicting. There's a concurrent write that was done, because when you wrote 1 to B, it was unaware of the 2 that was written to A. Similarly, when you wrote 2 to A, it was unaware of the write that was done to B. So these are concurrent writes or conflicting writes. Now, how will they reconcile this? So when A sees 0, 1, A knows, okay, B has done one write it was unaware of. So we'll just add that over here to 1. So what is the final X value? 2 writes from A plus 1 write from B. The X value here will be 3. Similarly, B will see, okay, it was unaware of 2 writes done by A. So we'll just add 2 here and 1 write of itself. So X value here will also be 3. So for this distributed counter example, the X value is nothing but the sum of the values at each index of the version vector. So how did they reconcile 2, 0 over here and 0, 1? The final version vector is the max at each index. So here it's 2 and over here it's the max of 0, 1, 1. So the final equivalent version vector in both these nodes will be 2, 1 and 2, 1. Now let's say A gets another write and its version vector will increment just its index, will be 3, 1 over here. And let's say B also gets a write, so it'll update its index, so it'll be 2, 2 over here. Now again, this is a concurrent write because B was unaware of the write that just took place on A's node and vice versa. Now when they try to reconcile, how will they do it? So 3, 1 and 2, 2. So A sees that, okay, B has done one write, so it'll update its index over here to 2. And B also sees that A has done one write, so it'll update its index over here to 3. So both the vectors, the version vectors of both the nodes will be 3, 2 finally, 3, 2 and 3, 2. So over here, the way we derived to the final version vector was to just take the max at each particular index. So now the X value is pretty easy to derive. It's just 3 plus 2, which is 5. X is 5 and X is 5. So I hope now you understood how we came to the state 3, 1 and 2, 2. What is the physical meaning of this, and why are we taking the max of each particular state, and how are we deriving the X value from the version vector. This is a distributed counter example. It's pretty easy example. Over here, X value is nothing but the sum of each particular index value. Let's take a look at another example, which is more realistic, where we deal with writes, writing some string to an ID like ABC. So let's take a look at this case. You have a DBA over here and you have a DBB over here, and you're writing X is, let's say, ABC and X is XYZ. So the version vectors over here were 1, 0 and 0, 1. Now when it comes time for replication, you know that there's a concurrent write over here. B was unaware of the write that took place on A. So how will they resolve it? This is not like the counter, we can just add values. So what should the final X value be? So one resolution for that is, let's store the sibling values. So X will be ABC, comma, XYZ. So both these nodes will store both the values of this for X. So the next time a user tries to read the value of X, that user will get a choice. Hey, which value do you want to finalize, ABC or XYZ? And the user will say ABC and you will discard XYZ. So let's say you had ABCXYZ over here and ABCXYZ over here as well. And the final version vectors were 2, 1 and 2, 1. You have a user that comes in and the user selects ABC. So you'll discard XYZ over here. So this version vector will be 3, 1 with the X value being ABC. This version vector is still the same, 2, 1 with ABCXYZ. So after some time, when this tries to replicate, this node sees that, okay, the version vector 3, 1 is obviously greater than me. So this node clearly has the latest and greatest value of X. So it'll also update itself to just ABC and discard XYZ out. So the first solution to deal with concurrent writes is store the siblings for the same key and leave it to manual intervention to help restore the write conflict. So next time there's a read, we ask the user to make a choice and delete the other value and increment our own version vector. And obviously our own version vector will be in the latest and greatest state. The problem with this is this works fine if you have a small to medium size application, but if you're prone to write conflicts, if there are multiple writes and you have a large number of nodes, always having manual intervention is not a great idea. By the way, a version vector will be maintained for each particular object, each particular table row. So let's say your row has ID, name, age, and you have an update to just age. You're changing it over here. So let's say the original vector was 2, 1, and then because you change the age, the vector will change to 3, 1, and you will ship the version vector with the row to the other nodes to be replicated. Now, if you have 100 nodes, the length of the version vector is also going to be 100. So it's 100 here times 100 because you have 100 nodes. So you have 100 of these 100 elements across your system. And this will obviously be inefficient when you talk about scale, especially because you'll have a lot of these version vectors plus these rows being shipped across the wire every time there is a replication happening. So in terms of efficiency, in terms of bandwidth consumption, it can be a little bit of a cause of concern when you talk about multiple nodes in the picture. Another approach is to resolve the merge conflicts automatically. So what we do is we write some algorithm with some data structure and we tune it to a specific use case. For example, one use case, the example you just saw, was to update the product name, let's say XYZ. So you create a data structure, your own data structure plus your own algorithm specific to that use case that will help resolve merge conflicts. So we call that data structure plus algorithm combination a CRDT, which is an automatic approach for merge conflict resolution. CRDT stands for conflict free replicated data types. So you're creating a data type, a data structure with some algorithm to help resolve conflicts in a replicated setup. So the way CRDT works is you send your CRDT data structure, it would be a vector, set, list, map, or some complex structure, and then just merge your local version, your local CRDT with the broadcast one. So the CRDT, when you create your own CRDT for your custom use case, you'll obviously be associating it with a data structure, plus you'll be writing a merge algorithm. Now that merge algorithm should satisfy 3 properties. The first one is commutativity. So in commutativity, the order in which you process the replications coming from the other nodes, the end outcome should be the same across the different nodes. So let's say you have one node over here and another node over here. This first node first receives the update from node B, updates its state, and then receives an update from node C and updates its state. So let's call this final update after processing the CRDT from B and after processing the CRDT update from C. Similarly, parallelly, you have another node that first gets the update from C and then gets it from B. So the final outcome after performing the updates should be same. So that's the commutativity property. F of A comma B should be equal to F of BA. The order in which you process the writes should be, the end outcome should be the same, because you're talking for distributed setup. So even if you do send B first and you do send C afterwards, what if B were pretty far away from this particular node? You could have C that reaches this node first, and then you can have B that comes in later. So you can't predict the order in which writes come to a particular node. So it's very important that the merge functionality satisfies commutativity. So on a related note to commutativity, it should also satisfy associativity. So the final result is same irrespective of the order in which a local node performs the merges. So if you're merging, let's say, the update from A, B first, and then using that outcome, you're merging the update from node C, the end outcome, let's call this X. So let's say another node will first merge the update from B and C, and then it'll merge the update from A with this outcome. So the end outcome should be X again. So the order in which you perform merges should be immaterial, and the end outcome should be the same across nodes. And the third one is also pretty important. It should be idempotent. So let's say you get this particular update from a node A, and for some reason you get this update again. So when you get this update again, your state should not change. It should be like you've only processed the update just once. When is it possible for you to receive duplicate updates? It is very possible in a distributed setup. Let's say the node thinks that the node is waiting for your response after receiving the first update, and you sent a response, but the response got dropped midway, it got lost. So the node will send you another update. For instance, let's say the node sends you increment X by 1 and you process it. So your X value is now 5 and this is correct, but you fail to respond to it, and now the node sends increment X again. So you should implement your merge functionality in such a way that you don't process X, you don't increment X again. So this should be X is 5 only. You should safely discard this message. So obviously, to create a CRDT structure that honors all these three criteria is not very trivial. And when you talk of creating your own custom CRDT structure for your specific use case, you'll most likely write a research paper to mathematically prove that whatever algorithm you're developing follows these properties. In this video, we'll not take a look at any complex real-life CRDTs that are in use. We'll take a look at very basic CRDTs, very basic structures that solve very primitive use cases. Once you go through this video, I would encourage you to go through a high-level design video of Google Docs. CRDTs are used in real-life, real-time collaboration tools like Google Docs. So if one person writes A, B, C, and another person on that same line wants to write X, Y, Z, how does Google Docs automatically merge the final state? How does it do conflict resolution when you have conflicting updates? All that is done through CRDTs, and the data structure that we use is very complex. So let's limit ourselves to some basic CRDTs. The first one is a G counter. So G counter is a grow counter. So if you have a use case where you only want to track increments that happen, for example, a distributed counter, you will be using G counter. So G counter is used when you want to count events or actions in a distributed setup where only increments happen and you never have to decrement. For example, YouTube's views counter. So one node will track that, okay, a new view came in, so the current view is 100, and then another node will track, let's say the original view count in both these nodes is 90. So let's say 10 views came in over here, and let's say 5 views came over here. So over here it's 95. So how will these two nodes sync up to know that we have 15 new nodes come in? So this can be taken care of with the help of a G counter. So G counter, the data structure that you're using is basically a vector, like a version vector only for all intents and purposes. So node A will have its own version vector over here, node B will have its own version vector over here. And when they sync up, the final version vector is basically just 3, 5, as we saw earlier, how merging happens in version vectors with concurrent updates. So the final view count will be 8. This is exactly same as the distributed counter example that we saw. So we use a G counter over here. The merge operation, how can you prove that it is associative, commutative, and idempotent? So it's associative. Let's say you get 3, 0, and 0, 5. The final outcome is going to be max of 3 and 0, which is 3. The final outcome is going to be max of 0 and 5, which is 5. Let's say node B, whose local version vector is 0, 5, then gets this 3, 0. So again, the final version vector after merging will again be 3 and 5. So this is obviously associative in nature. It's commutative in nature, I mean. Similarly, this is also be associative. When you talk about 3 nodes over here, let's say the version vector has 3 slots, and let's say you merge the version vectors coming from A, B, and then you merge the version vector coming from C. the end outcome is going to be the same as if you were to merge the version vectors coming from BC first and then from A. The end outcome is the same, so it's associative as well. What about idempotency? Let's say you merge the version vectors and the final state is 3, 5. And now let's say node B gets again the same update from node A. So let's say node B again gets 3, 0. But if you were to use your merge function for version vectors, you just take the max. It's again going to be 3, 5. So even if you were to get the same update again, the end outcome is not changed. So it's still going to be 3, 5. So obviously this operation is idempotent in nature. So this was our first CRDT that we saw, which is a G counter. G counter basically uses a version vector as the data structure. And the way that we are merging concurrent updates honors the associativity, commutativity, and idempotency properties. So let's say along with increments, you also want to support decrements. Say for instance, on Reddit, this is the post, you will be able to see the upvote, the vote ratio. So if you get 10 upvotes and you get 5 downvotes, what you see over here is 5. This is the upvote / downvote count, and you'll be seeing the upvote percentage as well, which in this case is like 66%. So what you'll do for supporting both upvotes and downvotes is you'll make use of 2 G counters over here. One is the upvote counter, the increment counter, which is your, let's call it P, positive, and another vector, version vector, for your downvotes over here. So if you get a version vector that gives you 1 and 2 over here, and you have a version vector that is 2 and 3, and this is your local state. Let's say it's 1 and 1, and this one is 2 and 2. Your final version vector after merging for P will be 1 and 2, and your final version vector after merging will be 2 and 3. So what is the total number of upvotes you got? 3, and the total number of downvotes is 5. So what you'll display on Reddit's post is -2. So it's a heavily downvoted post. So the same properties for the merge functionality holds true over here. It will be associative, commutative, and idempotent as well. Let's take a look at the third use case, which is a G set, a grow set. So a grow only set is a CRDT where elements can only be added. So you're adding these strings to a particular ID. So the use case can be when you only want to add stuff and not remove it from the set. For example, if you want to maintain a log of all the users or devices that are connecting to your system, you will have this particular G set over here. So if you have your application and you get new devices that come in, the set will only keep increasing. It won't decrement because these are new devices that are getting connected. So let's see how do you implement this. So let's take this example. You are running a chain of pet stores where you are basically selling pets. And the first node, the first pet shop, records that you've sold a cat and a dog as pets. And the second pet shop records that you've sold dog and a fish as pets. So overall, when you have to merge it to keep track of what all animals you've sold, the end outcome is going to be the union of these two sets, which is going to be cat, dog, and fish. So here the data structure using is a normal traditional Java C++ set. And when you perform union of a set, a merge of a set, you'll only get unique elements in the output. So this is obviously going to be idempotent, commutative, and associative. Idempotent, cat union cat is going to be cat itself. You can have just one element cat in the set. And you can prove by basic intuition why it's commutative as well as associative. Now, what if you also want to remove items from the set? So let's say you want to maintain an active log of what are the current users in your system, current devices in your system. So two-phase set allows adding and removing elements. So you'll maintain basically two sets over here. One is an add set and a remove set. So let's say a shopping cart example on Amazon, you've added apples and bananas. But let's say a minute later you decide you already have bananas at home, so you remove the banana. So you in the remove set, you just add banana over here. Now, just from node A's perspective, what will the final outcome be? It'll be apple, banana minus whatever is in the remove set. So it'll just be apple. And this is good. Now, let's say in node B, the add set also has banana and carrot, and there's nothing in the remove set. Now, when you perform the union, the final outcome will be apple. The final outcome will not be banana because banana is in the remove set of 1. Even though banana is in the add set of node B, but because banana is in the remove set of one node, you're not adding banana in the final outcome. And you'll have carrot over here as well. So I don't know if you observed this, but a key point is once an element is removed and it is part of the remove set, it can never be added back. So this could be a possible drawback depending on your use case. So again, this is going to be idempotent, commutative, and associative. These are basic properties of sets. But let's say if I remove a banana, I should also have the option to add back banana again. Over here, this new node is again adding banana. Let's say after 10 minutes on my mobile phone, I'm adding banana. Now I want banana back again. So how will I ensure that banana is in the final list? So for that, we make use of another CRDT type, which is called the OR set, which is observed remove set. So it supports add, remove, and re-add. So in OR set, whenever you add an element in the set, you will append it with an unique ID and only then insert it into the set. So here Alice's phone, she adds Apple with, and she appends a unique tag A1 with that Apple item and only then puts that into the set. Same thing with banana, tag A2. Alice's tablet has banana, tag B1. So again, you have banana, which is a duplicate product over here, but it comes with a different tag. It's a different node, and carrot over here. Now let's say Alice's phone decides that, okay, I added banana, let me remove this banana. I don't want it any longer. So in the remove set, you will add banana with whatever tag there is in this set, which is tag A2. And then Alice's tablet decides, no, I want that banana again. So she will have banana again with a new tag. Now, when you finally merge it, what you'll have is apple with tag A1. You'll have carrot with tag B2. You will see that you have banana tag A2, which is in the add set, and the same thing is also there in the remove set. So you'll totally discard this. But then you'll also see that banana is also there in the add set, but it's with a different tag. So you'll again add banana over here. So you have apple, banana, and carrot back again. So this is how an OR set works. Let's take a look at another CRDT, which is the LWW register, last write wins, and it keeps only the latest value based on the timestamp. So obviously you're dealing with physical timestamps, it is susceptible to clock skews. A better approach is to use logical timestamps, and we'll go into more detail on logical timestamps using version vectors, vector clocks in the next video. So if you use physical timestamps, it's susceptible to inconsistencies if the nodes have unsynchronized clocks. So let's say node 1 over here sets the preferred color to blue at 10 a.m. and you have a concurrent write on node 2 where the preferred color is green at 10:01. So when they replicate, your merge algorithm will choose the preferred color based on the last write. So the last write over here will win. So just to bring home the point, where are version vectors used? Version vectors track causal dependencies and they help detect if you have conflicting concurrent writes. Version vectors work at the object or row level. So let's say your row over here has multiple attributes, ID, name, age, gender, whatever. And if any one attribute changes because of a new write that comes in, you will update the version vector corresponding to this object, corresponding to this record, and ship the entire row with the version vector to the other nodes. In contrast, CRDTs are finer grained if you choose to have them that way. So each attribute over here can be associated with a CRDT. This can be associated with a grow counter. This can be associated with a grow set, so on and so forth. Let's take a look at one example over here. So this is an object where the name is Amanda and the preferred color can be a grow set over here, green, blue, and like or dislike can be a PN counter. So CRDTs in this case can be much more finer grained, and for the same object you can have a combination of other CRDTs. So in conclusion, version vectors help detect causal dependencies and to identify concurrent writes. When you have conflicts over here, there are two ways to resolve these conflicts. One is using manual intervention. You ask the user which value do you want from the sibling values and you store only that value. Another way is to use last write wins using physical or logical timestamps. CRDTs eliminate conflicts through purpose-built merge functions depending on your use case. So CRDTs are basically specialized data structures for automatic conflict resolution. Think of Google Docs. So there are some applications where CRDTs in a way use version vectors by themselves. The line is very blurry, like the examples we saw for the counters, the grow counter, the PN counter, using a version vector over there. But some use cases, some merge config resolutions that are automatic in nature, you don't use a version vector, you use data structures like sets or lists. In that case, you want to implement your own merge functionality. You can't rely on a version vector over here, that it won't help. So the lines, the distinction between version vectors and CRDTs can often become blurry, but understand that CRDTs are more complex data structures that you custom build for specific use cases, while version vectors are a general purpose data structure that you use to detect causal dependencies and concurrent updates. Let's end this video with the final replication setup, which is leaderless replication. So in leaderless replication, you can read from any node, write from any node. There's no node which is a designated leader. There's no concept of leaders or followers over here. Any node can accept reads and writes. So we write to many nodes typically, and we also read from many nodes. This is to ensure quorum consistency. Now, if you recall in the multi-leader setup, if this is the leader node and these are its followers, in order to avoid lost writes, when you get a write update to the leader node, you will first select a portion of the follower nodes to write into. You will synchronously replicate it over there and then immediately send a commit success message to the user. So let's say after sending this, the leader goes down. No worries, because our write is not lost. One of our followers can kick back in through raft consensus. Now, in this multi-leader setup, if you're aware, the quorum consistency mandates that the number of reads plus writes should be greater than n. Now, in the multi-leader setup, when you choose the follower nodes to write into, you can be pretty relaxed in your quorum constraints. So your read can be even just one or two nodes. That's more than enough. All you need to ensure is at least one node has the write before you send a commit success message. And this is all done to prevent lost writes. Leaderless replication, on the other hand, takes it one step further. The quorum consistency should be typically very strict in this case, leaderless replication, because you don't have a concept of followers over here. You only have a bunch of independent leaders. So when you write, you will be writing to a quorum, and when you read, you will be reading from many nodes such that the reads plus writes is greater than n. In this way, you can avoid eventual consistency and you can guarantee strong consistency in almost all aspects. So strong consistency means after writing the latest value, all subsequent reads by any user, they'll read the same value. So here when you write to many nodes, and when you read from many nodes. You read from a quorum, you'll write to a quorum. This guarantees strong consistency, at least on paper. So let's say over here, the original version is version 1, x is 3, and then when you write, you will pick a majority quorum, which in this case is 3. So you'll write to these 3 nodes, and when you read, you will read from these 3 nodes over here. Now, because the reads and writes, they'll overlap over here. So when you are reading, you'll know that, okay, at least one node has given me a greater version. So this is going to be the latest and greatest state. So you consider x is 5. Let's see, when is multi-leader better than leaderless? Number one is the write latency. So in the case of multi-leader, typically you'll just write to the leader node and that's about it. If you want to prevent lost writes, then in that case, let your leader node replicate to one or two of its followers. You don't need to maintain strict quorum over here. So the latency is going to be pretty low in order to service write requests. In leaderless, when you write, you won't be writing to one node, you'll be writing to a quorum of nodes because you want to ensure strong consistency over here. So in that case, the latency will be pretty high. Now, quorums are typically not used in multi-leader setups. The only place where we use quorums is to prevent lost writes, and even then the quorum, the W number that we select need not be necessarily strict. It can be a very small number like 1 or 2 nodes just to prevent lost writes. In the case of leaderless setups over here, we need to write it to a majority of nodes and also read it from a majority of nodes. Again, back to the multi-leader setup. If this is the leader and you have the followers over here, when you get a new write, let's select it over here, let's select it over here, you synchronously replicate it to a small portion, update yourself, and then send the commit success message. So now if the leader goes down, no worries, because you've saved the latest write to some of your followers, and then these followers will do a raft consensus among them and elect who the new leader is. So this new leader will say, I have the latest state, I will continue to accept writes, and I will continue to replicate all my new followers and the other leader nodes that are there in the other regions. But remember that in a leaderless setup, you don't have the concept of a leader. So there's no raft consensus over here. So when you write, you'll have to write to a quorum. And when you read, you'll have to read from a quorum. And this is all done to ensure strong consistency. So if your application has strong consistency requirements, you'll be making use of strict quorum reads and writes. Now, in the availability setup, the multi-leader wins hands down, because if one leader goes down, no worries, you have other leader nodes as well, or you can elect another leader from whatever followers there are. But in the case of leaderless, if you have nodes that fail and you're unable to form a read or write quorum, then you stop taking in requests. So your system is not available now. And this is all done to ensure strong consistency. So if there are no quorums available due to network partitions, or if the node shuts down, and if you're unable to form a write quorum, if you're unable to form a read quorum, you will stop servicing those requests. Your system is unavailable. So availability is an issue in a leaderless. Another thing is throughput over here. Multi-leader scales with the number of regions. So if you want to service a new region, a new continent, just add in a new leader with its follower setup over there. But in the case of leaderless, you have these different regions and you have nodes in each of these regions. And if you have a write request that comes in here, you'll have to write it to the quorum nodes, which are located in other regions also. So your leaderless, the throughput in leaderless is bottlenecked by the slowest, or whatever the furthest away node is. Now let's see, when does multi-leader win decisively? In conclusion, geographic distribution. If we have our users spread across regions and we get very write heavy loads compared to read heavy loads, and if we favor availability over consistency, we make use of multi-leader. Obviously, we'll be using leaderless if with quorums, if we favor strong consistency. Our applications are very critical, like financial applications. In that case, strong consistency requirements are mandatory. We use quorums. We can use a leaderless setup where the amounts of reads and writes are balanced. So when is a leaderless better than multi-leader? Strong consistency guarantees. So in a multi-leader setup, let's say we have a US leader that says 100 units are available, Europe leader says 100 units available, and the Asia leader says 100 units available initially. Then at 12:01, you get simultaneous orders to US, Europe, and Asia. US gets 60 orders, Europe gets 50 orders, Asia gets 40 orders. And all these nodes will independently process. These independent leaders will make their own decisions, and they already know that the initial state is 100, and they'll accept these orders that come in individually. But at the end of processing these orders, these different nodes have promised 150 orders for only 100 supply. So this breaks the data integrity, this breaks the consistency guarantees of our setup. So for such situations where you don't want the invariants of your application to be broken, you go with the quorum model with replication, with leaderless setup. So in the leaderless setup, all nodes initially will show 100 is available, and then you get an order placement with quorum rights. So let's say the order goes to the US node. The US node won't make independent decisions. Before that, it will first send the write to the quorum nodes, which in this case WS3. So only after you send the writes to 3 other nodes, they'll decrement their value to 70. The order is confirmed, and that's about it. Now order 2, the European node gets an order for 80 quantity. Now the European node locally, it shows that there is 100 quantity available, but you won't just read from the European node. You'll also be reading from a quorum nodes. So you'll be reading from this, and you'll also be reading from this. Now you'll see, oh, the latest state is 70. So in that case, you will drop that write, you will fail that write. So another point that favors leaderless is you don't have to deal with a lot of conflict resolution nightmares over here. So you can avoid having CRDTs, version vectors for the most part. So let's take a look at this multi-leader setup. Before the network partition, you have 2 leaders which handle 10,000 operations per second. And then you have a partition of 6 hours, and both these leaders take independent decisions. You have split brain over here, and let's say there are 650 million operations over here, and they are concurrent writes. They are conflicting writes. So after the partition heals, you now have to resolve these 650 million operations. So over here, you have very high availability. Even though you had a partition over here, you still were taking in read and write requests. But at what cost? Number one is the reads that you do, they differ in value. So you won't be getting consistent reads across the different partitions. And number two, the collision resolution is going to be very expensive once the partition heals. In contrast, in the leaderless setup where we use quorum consistency, if you have a partition over here, and let's say this particular partition is unable to form a quorum, so it won't accept the write requests or the read requests. So here you are sacrificing on your availability in favor of strong consistency guarantees. So when the partition heals, there's no conflicts to resolve over here. All you have to do is quickly patch P2 with the latest data. So a quick summary, multi-leader is better when you have geographic distribution, users in multiple regions, and you have write-heavy workloads and low latency writes are important. When network partitions are pretty common because you have multiple regions over here, and you can tolerate eventual consistency. You use leaderless better when strong consistency is of utmost importance and when conflict resolution is pretty simple. You don't have to use version vectors or CRDTs. When you want operational simplicity, so there's no leader management, there's no failover, there's no raft consensus over here. So the bottom line is multi-leader. You use it when availability is of utmost importance, and leaderless, use it when strong consistency is of paramount importance. Let's take a look at how updates are propagated to the non-quorum nodes. So if this is node 1, node 2, node 3, node 4, and let's say you write x is 5 here, and 5 here. This is a non-quorum node. You don't have the latest version of x over here. So what do? One way is through read repair. So if you have a read that comes in, you'll obviously, let's say you read from here, you read from here, you read from here, and you understand that the latest version of x is 5, and one node that you read from does not have this latest version. So when reading only, you can just patch the this node with the latest version x is 5. So that's called a read repair. So after reading, you are repairing the non-quorum node. Another method is using anti-entropy. So entropy in physics means disorder. Your nodes eventually diverge away in terms of the information. They all get different writes. So this node will get writes for A, B, C. This nodes can get writes for E, F, G. So there's a disorder here in terms of the information they possess. Anti-entropy aims to fix this disorder by basically syncing them in the background. This is just a fancy term for ensuring that they all have the same information in the background. So how do you propagate this information? How does this node tell this node that, hey, we need to update ABC? And how does this node tell this node that you need to update EFG? So anti-entropy is a background process that detects and repairs inconsistencies in replicas. You can perform anti-entropy through any means possible. So one naive way is periodically let this particular node send all its entries, all its millions of records to all the other nodes, and those nodes will individually scan those records and check which update is missing, which update is new, which record is updated, so on and so forth. All this is obviously not used in practice. Another way to implement anti-entropy is with the help of the replication log. So if you recall, your replication log will contain a log of all the operations that you've done. So periodically you can just ship your replication log and all the other nodes can see whatever new writes you have done, whatever new updates you've done. But the problem with this is there's a lot of redundant overhead since we already have a lot of overlapping writes. How are we having overlapping writes? Because you're doing quorum writes. So it could be possible that all the other nodes already know of whatever operations you've done over here because they were part of the quorum write. So all you have to do was just send this new write that came to you to the non-quorum nodes. So rather than shipping this entire replication log, we can optimize it even further. And the structure that we're using is a Merkle tree. So in the Merkle tree, let's say that these are your initial rows, A10, B45, 6, C63, D7. So this is your key and this is the corresponding value. We'll take the hash for each of these rows. Let's say it's this 762 all the way to 438. And you'll try and construct a binary tree out of them. So in your bottommost layer, you'll have the hashed value of the records. We'll construct the next layer by taking the hash of this, So it'll be 574, this will be 626, and then the root node will be the hash of this and this. And similarly, let's say this is the node B, and node B will also create its own Merkle tree with whatever data it has. So let's say node A has A, C, E, F, G, and node B has B, C, D, F, G. So they differ in just one value, which is A and B. Now, because they differ in one value, this is A over here, and this should be B. You can observe that starting from the root node, the Merkle trees differ. Now, during the time of replication, node A will send its Merkle tree to node B, and node B will compare and check what all keys are differing. So I'll look at the root node and see that the values differ. So node B will know that, okay, something is different. Let's see what keys are different. It looks at the left subtree, looks at the right subtree, and sees that the right subtree is unaffected. So all these keys are fine. So there's no need to request these keys from node A. Then look at the left subtree and sees that, okay, 505, 574, there is some difference over here. Looks at the left subtree, which is 746. Right subtree is 127. Right subtree is fine. Then just boils down, narrows down to this particular key, which is 762 versus 746. And it will request for this particular key from node A. Node A will send it the key with ID A. Similarly, node B will also send its own Merkle tree over here, and then node B will also send the record with key B to it. And towards the end, they both will have B over here and A over here. They'll have the same data. They will resolve the entropy between them. So Merkle trees help quickly identify what keys we need to fetch from the other tree, from the other node. So if this tree has, let's say, X, but not Y, and the other tree, the other node has Y, but not X, by the help of the Merkle tree, we can quickly identify those ranges of keys with the help of the binary tree traversal, and we can only request for those specific keys and update ourselves with that. But let's say X over here in this node was written to be 5 and X over here was written to be 6. Now again, the Merkle tree will still differ because you're computing the hash, and the hash will differ based on the values as well. So in this case, your Merkle tree number 1 will tell you, okay, there is a difference in the data that you have, and there's a difference in the value of X. Now in this case, Merkle tree will just help you identify what values are different. Now you will fetch the value of X from the other node. So this node will fetch X is 6. Now this node still needs to perform conflict resolution. So you'll be making use of, again, CRDT or logical physical timestamps or version vectors in this case. So your merge operation has not yet escaped over here. You have multiple leaders, you have these multiple nodes accepting reads, writes, and because you have these independent nodes that accept writes, you're prone to merge conflicts in this case. So you will again be relying on timestamps or CRDTs for conflict resolution. So to not confuse ourselves, Merkle trees just help identify what keys, specific keys we need to be grabbed from the other node, rather than the other node sending their entire replication log or all the table entries and us manually parsing that. Just quickly identify what nodes, what keys differ. And once you identify those keys, let's say we also have a different version of that key. So you are sending me X is 5, but I have X is 3. Then in this case, we obviously have to perform some merge conflict resolution using CRDTs or version vectors or timestamps. Let's quickly end this video with the last concept, which are sloppy quorums. So in strict quorum, where read plus write is greater than n, those read nodes and those write nodes will be predetermined for a key. So let's say for the key X, you already have determined what the read nodes and write nodes should be in N1, N2, N3, N4. And let's say for another key Y, you've already determined some other set of nodes. How will you determine this? Using something called consistent hashing. And we'll talk about consistent hashing in the next video. So in strict quorum, replicas are predetermined for keys. Your quorums are predetermined. Example, for key user 1, 2, 3, your designated replicas are going to be A, B, C. What sloppy quorum tells us is, let's relax this parameter a bit. So let's say B over here is down, but I still need 3 nodes to fulfill the quorum. So let me find any available node. So in this case, I'll use D. So even though D was not the designated node for this key, I'll still be making use of it because sloppy quorums help relax that constraint a bit. So when a designated replica is down, the system will relax the designated replica rule and writes to whatever available node there is. Mind you, the reads plus the writes should still be greater than n. The number w will still be the same. You can't change that. It won't be relaxed. Just the node will be relaxed. The node can be different. And point two, temporarily accepts the non-designated replica to satisfy the quorum. So over here, D will temporarily take the place of B and start accepting writes meant for this particular key user 123. Then when B is up, all those writes that you wrote to D will be transferred to B. So when you write to D, you will say that, hey, this is just a temporary write. Your ultimate goal is to transfer it to B whenever B is up. So you will add a hint that your end goal is to push it to B. So once B is up, you'll be doing a hinted handoff. So it adds a hint to the substitute about the actual designated replica. And later when the node is back up, it performs hinted handoff. So D will push whatever updates it wrote in place of A, in place of B, to B. So the quorum size still remains the same. And again, why do we use sloppy quorums? The overall goal is for strong consistency if you make use of strict quorums. But let's say you prioritize high availability. So you have equal distribution of reads and writes for your application setup. It makes sense to use leaderless. But let's say your application is not very critical. It's not a financial application. And you prioritize availability over consistency. You're fine with eventual consistency. In that case, we'll be using sloppy quorums over here. Now the question is, how is strong consistency not maintained over here? We know that the read plus write is still going to be greater than n. So how are we saying that strong consistency can't always be maintained if we use sloppy quorums? And let's take a look at this example. So if n is 3, let's take our w to be r2 and r to be 2, and these are our original 3 nodes over here, a, b, c, and let's say node b is down. So if our system uses sloppy quorum, it tries to find any available alternate node. So if this is A, this is B that just shut down, and this is C. Now, assuming each of these nodes corresponds to one region or one continent, what is typically observed is it's better practice to have backups of each node in a region as well. So let's call it B1 and B2. So these are not followers, these are just data backups of B. So B will be serving users in Asia, and obviously these users will have a lot of cookies in them, their requests. So B will cache those requests, and you will occasionally replicate those user sessions, user cookies to B1 and B2, and B1 and B2 can service read requests as well. It doesn't make sense for B to store those cached requests, those cached data to A and C, because B, A, and C will service their own regions. So they don't have anything to do with the Asia region. So what we have in practice is data backups of region specific nodes. So let's go with this for now. Now in sloppy quorum, let's say your W is 2, your R is 2, and your original nodes are A, B, C. And if B goes down, the system will obviously try to find any available nodes. So in this case, it'll find B1. So when you do a put key x value v1, your intended node was A and B, but actually it goes to A and let's say B1. So B1 over here is the temporary backup node. Now, next time you get a request, get key x, let's say node B is now immediately backup, but your hinted handoff is not yet done. B1 is not yet done transmitting that x value to B. Now, when you read, you'll be reading from, let's say, B and C, which are the designated read nodes. Then you'll get a stale read, because we know that C was the non-quorum node for write, and B was the node that just came back up, but hinted handoff is not yet done. So there's a stale read here. So even though you're maintaining quorums, but you're still bound to have inconsistent reads over here. Again, this is an extreme edge case. Actually, technically speaking, you're not honoring this formula over here, because your n now is not 3, your n is actually 4 if you consider B1 over here. But in practice, if you use quorums and you honor this particular formula, you're bound to get strong consistency. In the next video, let's talk about partitioning and linearizable databases.